Welcome all. I hope you're not too complacent after lunch, trying to relax, because we start off with a little quiz. But first I want to know of you, who of you doesn't know what Gapminder does, what Gapminder is? Let's just see some hands. Okay, who of you don't know Hans Rosling? Hans Rosling is a... Hands up if you actually don't know. Okay. He was our founder and he was the face of our foundation. This guy, actually, with bubble charts. And since there's some people that don't know who he is, I'll just play a short video to get kind of an idea of what we do. Oh, we got audio.
First, an axis for health, life expectancy, from 25 years to 75 years. And down here, an axis for wealth, income per person, $400,000, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now, I'm going to show you the world 200 years ago, in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubbles show the size of the population. And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40 in all countries. And only UK and the Netherlands were slightly better off, but not much. And now, why start the world? The Industrial Revolution makes countries in Europe and elsewhere move away from the rest. But the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now we slow down to show the impact of the First World War and the Spanish flu epidemic. What a catastrophe! And now I speed up through the 1920s and the 1930s. And in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now, after the tragedies of the Second World War, we stop a bit to look at the world in 1948. 1948 was a great year. The war was over, Sweden topped the medal table at the Winter Olympics, and I was born. But the differences between the countries of the world was wider than ever. United States was in the front, Japan was catching up. Brazil was way behind, Iran was getting a little richer from oil, but still had short lives. And the Asian giants, China, India, Pakistan, Bangladesh, and Indonesia, they were still poor and sick down here.
So that kind of gives you an idea. We do data storytelling, in short. And normally our presentations are like actually telling the stories that the data show. But right now I'm going to tell you the story behind the data. That's what we're here for at Øredev. There's a lot of technical things happening there. But first, let's start off with a question, like I said. And we'll just answer with show of hands. How many of the world's one-year-old children today have been vaccinated against some disease? So if you think 80%, raise your hand. Okay, it's about 40% maybe. Who thinks 50%? All right. 20%? Okay. I think we've got something like 60, 20, 20, the ratio of answers. I won't give you the answer yet, right now, but we're going to have a look at how that actual data number, that single number, how we can collect that. So behind each number is our people, right? Data is it's in the end about people. We often forget it when we see a data table, but it's about often stories about love, like a couple falling in love together, and when they love each other so much that they start creating life together. They're like, we want to make a baby, and then they probably will vaccinate the baby. And 200 years ago, actually, couples might have gotten about 6 babies, but 4 of them would die before the age of 5. So we didn't really live in harmony with nature, as some people say. It was way back in the early days, and we died in harmony with nature. And as we got vaccinations, as we got better healthcare, we got industrial revolution, we were able to save our children. So around 1920s, 1930s, there were about 5 babies per woman, and only 1 of them would die. And you can imagine if you have 2 parents, 4 children, those 4 children grow up, and they all get 4 children as well, you get population growth. And that's what we've seen in the last 100 years. But as time went on, people started to get less babies, and even less babies died. So right now we're at a new balance where 2 parents get 2 babies on average, and thus population growth will start decreasing, and we'll end up with about 11 billion in 80 years from now. And that's kind of where population growth will stop. So that's pretty great, right? That improvement that we made, all of a sudden no more children dying. How horrible is it for a parent to have to bury their own child? And that's all, well, not all, but a big part of that is that we can vaccinate our children. So how does this event of this child getting a vaccination, how does that then get into these statistics? You might think, well, the doctor probably gives the vaccination and then goes into their computer where they have the patient records, fills out, this child got vaccinated, and all that data gets aggregated in the cloud, in a system, and we can perform all kinds of analysis on it and get out a statistic. That is the case, but nowhere near all over the world. For example, in Colombia or South Africa, we just don't have that kind of digital health systems. We have it in Sweden, maybe, in the Netherlands, like rich countries. There we have these systems. But it doesn't work in a great part of the world. So what do we do then? Well, we hire a lot of people and we go door by door, simply with a big questionnaire, and we ask questions. And to be able to do that, you can choose to only visit 1,000 households in a country, or you can choose to visit all of them. And there's a lot of these surveys being done all over the world just to get that data. For example, this is a picture of the census in South Africa. And in a census, they visit each and every household in the country. There's also smaller ones where they might only visit 10% or just 1,000 households, like I said. But in this case, that means that they visited 14.5 million households. And just for being able to do that, they hired 120,000 field workers, so people with these vests. They trained them, and for 2 weeks, they visited all these households. And in each of these households, they asked 225 questions. So a big pack of paper for each household, answer all kinds of questions. How old is your child? Did it get vaccinated? What is your job? Have you moved recently? All these kinds of questions are being asked. So it's a humongous undertaking to gather all that data. And actually, it's not entirely safe either. This was in 2016 when in South Africa they did a community survey, which is 10% of the households, still a lot, 1.5 million households. And 7 of those field workers actually passed away on the job. So people died just to be able that we can get that nice little data point in there. It's pretty crazy if you imagine it, if you think about it. So then when we have all these questionnaires, they get all combined and collected by national statistical offices, such as Statistics South Africa. And they do a lot of, first of course, a lot of data entry, especially if it's paper. You can imagine just a huge amount of work that goes into that. But they're moving on to do it digitally with PDAs. And they most often publish 2 types of data. There's microdata, which is a huge file where each row is 1 person or 1 household or 1 economic establishment, 1 company. And so that's very detailed, but it's a lot of data and you need to process it. It takes a lot of work and expertise to do that. And that's why they also publish aggregate data. And aggregate data is the kind of things that we know, like a vaccination rate, a life expectancy, a population number, these kind of things. Okay, so how does it get to us then? Well, we don't get it from Statistics South Africa. That would mean that we would have to get it from every single country for every single survey, and that is a lot of work. But luckily, we have all these NGOs and other organizations that collect all the data from the different countries and combine them and publish them as separate data sets. So there are still things that they have to do. There's some hard things, especially when combining from different countries. For example, in Palestine, when you look at how many babies are born per woman, they don't say it, but you find it somewhere in the definitions. It's actually only to married women, because there's a cultural stigma on having a baby when you're not married, while the data from Germany, for example, contains babies to any women, married or not married. So these kind of things are solved by all these organizations, and all of them have like their speciality, right? So the World Health Organization does health data, ILO does labor data, etc. So you think like, great, okay, they solved all the problems for us. But they don't, because each of them has their own format and their own semantics in which they publish. So I can show you some examples. This is CO2 data from CDAC. It's basically, it lives on an open directory somewhere on one of their servers. And if you go in, you get a tab-separated file with metadata on top. Countries are here, capitalized names, for example. That's one. These are population data from the UN Population Division, where they have a website where you can download Excel files, which all have their own formatting with metadata in them. World Bank offers a download of a CSV file or a zip file with CSVs or Excels in it, Excel sheets. But they also have an API, which is already great. That's not something that happens a lot. But there's problems with the APIs and versioning, especially of translations. For example, like they might update the definition of an indicator, but the translation comes 6 months later, and thus they have the wrong description with the wrong data. All kinds of. So it's not nicely done yet, and you really have to be accurate to be able to find these problems. And sometimes it's even like this is Transparency International, which publishes a corruption perception index. In 2009, they published it on this website, just in a table. In 2017, they published it on a different website. It's a different thing, so you can't just build a scraper for all of them. You have to write one for every single publication. And on top of that, they don't even call the countries the same. This was, for example, Laos in 2017, while in 2009, it was called Laos. So even within an organization, they are not consistent with the naming. So there's still quite a job to do there. And that's when we enter the Gapminder realm. That's when we start working. So we have a project called Open Numbers, in which we try to crowdsource the harmonization, so that's making sure syntax and semantics are the same, of global and local statistics. So I've shown you the World Bank and these organizations, that's global statistics, looking at country averages and these things. But we're also interested in getting specific statistics like on municipalities or even neighborhoods from Swedish cities or all over the world, really local statistics, because that's what speaks to people. Like if you tell a random person what the life expectancy is in Cambodia, people don't really care. Like you got to be a specific type of person to care about these things. So, but when you say, well, in Cambodia, in this neighborhood, people live way longer than actually you do here in your Swedish neighborhood, then like, wow, okay, I didn't expect that. Cambodia, I thought they were like somewhere middle income, but better than Sweden. Cool. That's at least the experience that we have. So, to get a bit technical, we within Open Numbers we have a project Data Kitchen, on which where we have a lot of Python scripts that perform ETL tasks. I'll explain what ETL means in a bit. And we have Apache Airflow, which is a batch scheduler which automates all these ETL tasks. So just to get an idea what this Airflow is, is an idea of the interface. We have different tasks, like first check dependencies of the data source, then download the data source, run the ETL scripts, validate what you had, and then push it to a GitHub repository. These are examples of tasks that we do. So what's this ETL then? First, you have to extract the data. So like I showed you, it's in all kinds of different forms. There's data APIs. There's web scraping that you might have to do. There's bulk downloads with CSVs or Excel files. And we also create our own data, so we have our own spreadsheets, Google spreadsheets that we scrape as well. And those are the easiest to do because we actually follow one format there. So after extracting, we have to transform it. There's several steps. There's first the syntax. Like I showed you, there's metadata, different. Some have years in the columns, some have years in one column. There's all kinds of ways that it can be done. So we have one shared syntax that we transform it to, DDF. And we have to write a custom Python script to transform that for every data set, just because every data set is different. There's no way to do it. And sometimes, like in the case of Transparency International, what I showed you, it's just too different, so we just manually do it. It's manual work, opening an Excel file or copying the table and just creating the data set manually, because each time they publish, it's in a completely different format. Now, after the syntax is stable and the same, we can look at the semantics. So we have a certain namespace in which all the semantics are the same. So, for example, what we call entity IDs, so geographies, all the countries, all the world regions, the sex, the genders, age groups, they all have the same identifier. So not that you have one data set, it's Afghanistan capitalized, the other one is AFG, like the ISO code for the country. All of them will have the same identifiers. And the same for all the indicators, all your variables. They also all need to be the same, because World Bank calls it total population, while WHO calls it population total. And for a computer, there's no way to know that these are actually the same things. So the way that we do it is, for some things, we have dictionaries, where we just simply say, well, this is a synonym of this ID, this is a synonym of the same ID, and we just translate it, basically. And sometimes we need to do manual mapping, because, again, manual work is needed because it can be quite difficult to see, like, okay, is this an age standardized indicator or not? There's quite some expertise that goes into that, too. And then finally, part of the transformation is calculating new indicators from all this data. So one thing that we can do is we have done our own research on population data. How was it back in the 1800s? Because the UN doesn't publish that. They want to only publish data that they are very certain of. Like, they're all like have this academic mindset. If there's a certain uncertainty, and we can't publish if we're not sure, because people might say that we lie or that we do things wrong. At Gapminder, we don't care about that so much. As long we mostly say, like, probably the error in people's heads is bigger than the error in the data. So that's why it's fine to publish it and use it. Until we find that that's not the case, then we can use it. And of course, we got to say, disclaimer, big picture, don't try to analyze it in detail. But most of the things that we do is we talk about the big picture. So we bridge those data sets that we researched with data sets of the UN, and that way we have a nice long time series. And we use the Python pandas library for the people that know about these things. And what we build are called recipes, which is our own format, declarative format to give instructions on how to transform all these data sets. I can show an example of one of them. So this is a recipe in a YAML format, where we have a couple of ingredients that go in our recipe. So certain data points. It's basically just tables that we get. What's the key to your table? What are the indicators in your table? And then we start cooking. Guess it's legible, right? I can make it a bit bigger. Then we start cooking with those ingredients. So we do certain things, like here we translate. So we do that translation process that I talked about before. looking at all the moving it to our namespace. Here, for example, we take the carbon emissions and make CO2 emissions from them by calculating with a certain or multiplying with a certain constant. Here we take the CO2 emissions and we take a population to calculate a CO2 emissions per capita indicator out of it. We have here a window operation so that you can see cumulative CO2 emissions of countries over time. So all these kinds of transformations we use to calculate new indicators out of existing ones that we get from other places. Yes. So at the end of this transformation, we've got a data set in our own format that we call DDF, and that's a data model for collaborative harmonization, same thing, of multidimensional statistics. So what does this multidimensional mean? It's quite an important thing for us. Here you can see the same indicator, the vaccination rate, on different dimensions. Like this dimensions is a term that is used in different ways, but we use it basically to describe the primary key to our table. So in this upper table, the dimensions are country, rural, urban, and year. So in Brazil, in the rural population in 2015, had a vaccination rate of 75, while the urban population had a vaccination rate of 83%. But we can add a dimension to it. This is called disaggregating. Instead of aggregating, like having a lot of data and moving it together in one number, we disaggregate. And we can look, well, the rural in the upper middle income section, what was their vaccination rate? Or maybe the rural in the lower income, or rural in the higher income section of the rural population. So you can really drill down into specific subpopulations to see, okay, what is the vaccination rate there? And you can make it as crazy as you want. Like here's gender, urban, rural, education level, income. It can be really a lot of dimensions that you can drill down into. So why is this important? Maybe you've heard of the Sustainable Development Goals. I don't know, show of hands if you heard of it. So these are goals set up by the United Nations, where in 2030, where the world has to be. Like, if you set goals, then it's easier to make progress, right? So they say in 2030, there shouldn't be any extreme poverty anymore. There should be zero hunger, and all these kinds of goals they set up. Back in 2000, we set up the Millennium Goals, and one of them was to cut extreme poverty in half, for example, and we actually succeeded, like before the timeline even. And now in 2015, they set up the Sustainable Development Goals. And one of the things that is part of it is leave no one behind. Because as we progress, as countries get better, as you might have seen in our bubble charts, the world is getting better on average, but there's still pockets within those countries that are left behind. So even though you might see an average of, oh, this country has a vaccination rate of 90%, it could be like this rural, low-income people with low education. That's actually where there's still a very low vaccination rate. And by doing these disaggregations, we can pinpoint them with statistics to see, like, this is where we should go. Or maybe we should be in the cities. Is it rural or urban? So this disaggregation helps us to see where are still the hot pockets of problems where we need to go and fix things. So that's why it's important to do these disaggregations. And another thing that we do with the data, what's important in this DDF is that we have tidy data. And what that means is basically that every column in your data set is a variable, and every row in your data set is an observation. So all of these are not tidy. For example, here in the region one, we've got two variables in one column. You've got both the country and then the type of, if it's urban or rural. In this one, we've got two variables spread out, basically pivoted, if you know Excel pivot tables, pivoted up to the variable name. So here you've got vaccination, which is the indicator, and urban or rural in the columns. This is a so-called entity attribute value format, where you have an entity, so Brazil, for example, an attribute, their vaccination rate, urban, or it could be population under here and life expectancy, and then the value of that indicator for that entity. Also not tidy data. And lastly, here we have the variable of year spread out over the top row again. So what is the right format then to use? This. So one variable for each column is one variable, country, rural, urban, year, and vaccination, and each of these is one observation. And this actually influences what kind of, how easy it is to make visualizations with these things. So that's the format that we're going for, and I implore you to if you make data sets, try to follow this format too. It's a format also, it's set up by the creator of ggplot, Hadley Wickham. He also really pushes this format. So that was transformation from the ETL process. Then we start loading. That's the final step. So we validate first the resulting data set. We've got a command line tool that does that. And that same tool, we also have a graphical user interface for. So you can choose a data set and try to validate it. And you get data set is valid. And you can even right away visualize it in this offline tool that we made. We'll show you more of that later. Then when it's a valid data set, we push it to our GitHub organization where everyone can download all the data that we make for free. Please use it, and it's all nicely harmonized instead of having to download it from World Bank and WHO and fixing up the mess yourself. And we load some of these data sets in a database that where we have a public API so that you can even more easily get this data. So that database we call the waffle server. That's the next step in the pipeline for our data. It's a statistical database, like I said, with a public API. And it's JavaScript and TypeScript running on Google Clouds in a Kubernetes cluster so that it can easily scale if there's more demand on it. And inside of it, we had a Mongo database running. That didn't work as we expected, so now we moved back to just a couple of CSV files on S3, which is nowhere near a perfect solution. So we're really looking for trying to find what is the right way to solve this, how to build this statistical database and have it scale nicely, do all the things we want. That's a project that we're really working on now. It's a good challenge. So after that, we've got all our data in a database, and it's time to visualize. So we built a JavaScript visualization library called Visabi. And basically what this does, it speaks both data and visualization, and it does the translation for you. So you can talk to the waffle server or a different DDF data set and get data from it. That's what Visabi does. And all you have to do is talk visualization language to Visabi. And I'll explain exactly what that is in a bit. In Visabi, animation is a first-class citizen. It's really important to us because one of the problems that we see often is that long-term trends are overlooked, and animation is the way to make them insightful, to map time on time, so to say, and show how progress happened. And the charts that we built are all relying a lot on D3.js. So just a little schematic. You've got data and data readers. There's an API to the core. And then we've got an API to the charts and the dialogues, basically the views. So what is this visualization speak? Or visualization grammars, as they're called. Basically, the first time someone came up with a visualization grammar was this book that you see there, The Grammar of Graphics by Leland Wilkinson. And before that, people just thought bubble charts, line charts, all kinds of charts. They're all separate kind of things. But he thought, okay, well, can I come up with a grammar that, in a generic way, can describe these visualizations? And the other libraries that you see here, ggplot, that's used in R a lot, or Vega, they've taken his work and added it improved it, and built visualization libraries on it. We do a similar thing with Wasabi. So what is that grammar then? Well, each visualization contains two things. First of all, a marker or a geom. And these are just symbols, glyphs, or icons that represent a data point, that represent one row in your data, in your table, basically. So that can be a line, that can be a bubble, like we have a lot. It can be a bar, it can be just a label of text. Any of these things is a marker. And each of these markers have attributes, and you can visually encode data in those attributes. It's a little bit dense to say it that way, but think of it if your data has a low value, like a 0, you've got a very small bubble, while if your data has a very high value, you've got a big bubble. Or you can change the length accordingly to your data, or the angle of a line, the color hue, any of these things you can visually encode data to a certain property of your marker. So let's look at an example. The chart that I showed you before. So what are the markers here? Anyone an idea? What is the marker? What is the geometric object? You can shout. A circle, yes. Very good, Kai. So we've got a circle, and although the axes are gone here, we know that, like Hans explained to us before, on the x-axis, so on the bottom, we've got the income per capita encoded into the x position of the bubble. And life expectancy is encoded into the y position of the bubble. The population statistics are encoded into the size of the bubble, or actually, it's the radius of the bubble. The color of the bubble is according to the data of what world region that country belongs to. So this is kind of a simple example, but even this is a data visualization, in a way. A map, like with height lines and everything, is a data visualization. So you've got lines, for example, as markers. You've got texts as markers. So this text, for example, Matterhorn, it encodes the latitude and the longitude in the position on the map. It encodes the name of that location and what text it displays. But for example, also the height is encoded in two ways. There's markers, the line markers that show the height data in the map, but there's also these labels that encode exactly the same data. Probably in the underlying table, it's the same data, but they're encoded in a different way on different markers. So that's a little bit to give you an idea how to talk generically about visualizations. And when we go back to that tidy data that I showed you before, that's also why we like tidy data so much, because it's one observation is one marker. If you would use, for example, let's say this one, then it's hard to how do you call it? It's hard really to draw a marker out of that. I can't really come up with the example right now, but trust me. So we like that tidy data format, and from it you can even, like, if you want your data to be in one of these other formats, it's pretty easy to move from tidy data to one of the other ones, while moving back is actually quite hard, because this is one indicator name that actually has two variables, and you need to do like textual analysis on it if you want a computer to do it automatically. Same with this format, for example, or the format up here. So tidy data really helps in building your visualizations there. So we've got a visualization, and we just need to serve it. So for that, we have Gapminder tools. You can visit it on www.gapminder.org/tools. And it's basically a web app, quite lightweight, that configures Wasabi to connect to certain DDF datasets. And yeah, basically just a web page where that implements the library. And next to that, we also have an offline version of it. So that's an Electron app that I can show you here. You can install it on Linux or a Mac or on Windows, so you can work offline with all the data. And on top of that, you can just create a new chart with your own data, so with a CSV file or an Excel file, as long as it has the right format that we discussed before, the tidy data format. You can create your own moving bubble charts really easily using this. And we'd love to see what you do with it, so please contact us and tell us what you did with it if you are using it. So let's get back to the question that we started with. How many of the world's one-year-old children today have been vaccinated against some disease? So let's look at a big picture. We've seen all the tech stuff. What do we actually do with all this data that we collected? So, of course, we build charts with it. So we have data from WHO, which we can actually show and show you the right answer. This is how the vaccination rate over time changed until right now we're actually at 85%. So the 80% was even a little bit on the low side, just to make sure if people say, like, yeah, but that data has uncertainty. Yeah, we asked 80%, so 85 so 80% is definitely a correct answer. So when we have that chart, let's see, full screen, yeah. Yes, let me enter my password. Sure, Google. I can do that. Okay. Yes. So, like I said, correct answer is 80%. But actually, when we tested this, and this is what we do with all these questions that we have, it's one of the main projects that we perform at Gapminder. We see that people answer pretty badly. You guys were pretty good. 60%, from what I could say, answer it correctly. But when we look at representative samples of countries, when we ask these questions through polling companies, this is what we get back. Sweden was the best, with 21% only getting the right answer. And this is on a multiple choice question with 3 answers, right? So even if you say, yeah, I didn't know, I just chose randomly. Yeah, if you chose really randomly, you would get 33% of the time the right answer. But it's always worse than random. If you would go to the zoo and give a chimpanzee 3 bananas, they would get the right answer more often than you. Everyone gets beaten by the chimps, and it's a horrible thing. So what is happening here? We think there's misconceptions that people have. There's preconceived ideas that people use, so wrong knowledge rather than absent knowledge to answer these questions. So this is part, we even went to experts, like the World Health Summit. They answered worse than random on a question on health. It's pretty crazy. So this is part of, we have 3 steps of what we do big picture style if we don't just look at data. We've got the ignorance project in which we try to find these kinds of misconceptions. Where are the gaps in people's knowledge? Then the next step is Gapminder School. We replace these misconceptions with fact-based frameworks. So you've got probably wrong simplifications in your head. You think the world is divided in 2. There's poor and rich, and the poor people don't get vaccinations. And I see on TV there's a lot of poor people, so they get a lot of babies. All these kinds of generalizations, simplifications, and we try to replace those wrong simplifications with correct ones. So actually the world is getting better. Most people are not extremely poor. Most people live in the middle. About 5 billion of the 7 billion people in the world are on a middle income globally, and from a global reference frame. So all these kinds of things we teach in Gapminder School. And we also teach factfulness. And that way we want to prevent future misconceptions. And factfulness is the idea that, just like mindfulness is being aware of your thoughts, of what's happening in your brain, factfulness is doing exactly the same, being aware of your brain when you're trying to make sense of the world, when you're trying to create a picture of the world. So being aware of all the biases, especially, that you have. So when you see a new number and it contradicts what you already knew, you're like, oh, wait, but I have a confirmation bias, so I should probably not be as critical as I tend to be towards this new number. I should just be open to this new data that's coming in. So why is this? Because even misleading worldviews can be constructed from correct facts. Fake news is a problem maybe, but it's not just the only problem. Even if you have correct news with correct facts, you can get a wrong worldview. So, yeah, you can see it here, all correct maps, but put together you get a completely weird, like, is that Australia or, I'm not sure. Yeah. So what's happening there is the same as you would have in optical illusions. Your brain tries to make sense of the world, but in the assumptions it makes, it gets certain things wrong. And we've collected those things that go wrong in 10 dramatic instincts that we tend to have. We think in gaps, we think in binary ways, poor and rich, bad and good, Republican and Democrats, like any of these things. We think that the world gets worse often because we have a tendency for the negative things. We don't compare sizes of numbers. Any of these instincts all influence how you perceive the world. And to counter those, we have rules of thumb that you can apply to actually correct for all these instincts that we have. So we released a book in April, and I really recommend reading it. It really like changes how you see the world and how you perceive all the information that's coming to you. We try to push it and this to be part of national curriculums and yeah, because we think that's where really the change can happen, by teaching people how they can create a worldview rather than changing the media or any of these things. So that was kind of then the story, coming all the way from the love of the couple to you perceiving the statistics that were gathered from all these people all over the world, all the stories of all these people. So if you want to contact us, go on our websites, go on social media, look at our GitHub repos. And if you want to help us out with any of these things, if you're interested, then send me an email or talk to me or Angie down there during the conference. And it would be awesome. It's all open source. We're also looking for people to help us out more professionally. So yeah, please help us make the world a more factful place. Yeah, we are hiring. Sure. All right, thank you so much.